This is Applied Calculus, section 2.4, titled The Derivative. We're going to now take the concepts that we've been discussing in the beginning of chapter 2 to define an important concept called the derivative. And in calculus, the derivative and the phrase rate of change are used often interchangeably. And rate of change we should be familiar with from an algebra class because it is also used to describe slope. And you'll find that there'll be a connection between derivative and slope as well. So in this first image, we see a tangent line, and that tangent line is going to represent the slope of a curve at a particular point. So slope is reserved for lines, but we can see that this line, we can draw a bunch of different lines along a curve that describe the direction of the curve. And generally, when you solve for slope, you need 2 points, but we will be able to calculate for slope given a singular point using all of the concepts we've discussed in chapter 2 so far. One of the very important applications of slope is velocity. And again, velocity comes back to rate of change. Rate of change does not only need to describe items in motion. There could be a velocity to the population growth. There can be a velocity to your company's profits. So that phrase, velocity and rate of change, they can apply to things outside of physical motion. We begin with a definition for average rate of change. Average rate of change is calculated using 2 points. So this is the traditional slope of a line through 2 points. Now, we may not recognize this as the slope between 2 points, but what if I said we had a point whose coordinates were x1, y1, and we'll call that point 1, and we have another point, we'll call it point 2, whose coordinates were x2, y2. You would tell me that slope is equal to y2 minus y1 over x2 minus x1. And that's from an algebra class. But now, we've already said that the variable y is the same as evaluating f of x. They're interchangeable. So point 1 could be expressed as x1, comma, f of x1. That means we took the x1 value and plugged it into the function to get the y value, but we're expressing it with function notation. And we can say that point 2 is x2, comma, f of x2. And we say, great, okay, now we've gotten rid of the y's and we have the f of x1 and f of x2. But let's go further. Suppose we let x1 equal x, and suppose we let x2 equal x plus h, where h is the distance from the x1. So if I were to draw a horizontal number line, the x-axis, and we said, let's say this was the location of x1, and this was the location of x2. Then to get to x2 from x1 would be a distance of h. So to get to x2, we would first say, let's go to distance to x1, then the distance h. And that's what allows us to say, express x2 as x1 plus h. H is the distance between those 2 points. Well, then that redefines our points again. Point 1 becomes x, because we said replace x1 with x, and f of x. And point 2 becomes x plus h and f of x plus h. Remember how we did the slope formula before? We took y2, so right now this is our y2, and subtracted y1, so that would give us f of x plus h, subtract f of x, over, and then we took x2, x plus h, and we subtracted x1 minus x. And when you do this, do you notice that these x's will cancel out with each other? And now we have our slope is f of x plus h minus f of x all over h. And we say, well, that matches what we have here. And now they're letting x be replaced with the constant a, and we can get that and see we get the same formula. So this equation is nothing more than the slope formula from algebra, and we've changed the notation from x1, y1, x2, y2 to function notation, and then we expressed x2 as a distance from x1, and we get this slope formula. And the slope formula will represent average rate of change because it uses 2 points. So we have an example here. It says the revenue in dollars from the sale of X plastic planter boxes is given by this function for revenue, and it's defined on a domain from 0 to 1,000 inclusive, and it is graphed in this figure down here, figure 2. What is the change in revenue if production is changed from 100 planters to 400 planters? Okay, so that means we want to take R of 400 and subtract R of 100, and that's how you calculate the change in revenue from 100 to 400 planters. So R of 400 would be 20 times 400 minus 0.02 times 400 squared. And then we can find R of 100. And if we subtract those two, we get 3,000. So it'd be a change in revenue of $3,000. What is the average rate of change in revenue for this change in production? So this is, remember, whenever we evaluate a function, these are our y's. This is y2 minus y1. I need to find out what x2 minus x1 is equal to. Well, that's 400 minus 100. That's my x2, and there's my x1. And that would give me 300 in the change in production. So to find the average rate of change, we take the change in y and put it over the change in x, and that gives us 3,000 over 300, which gives us an average change of 10. So what is the average rate of change in revenue for this production? The average rate of change in revenue is $10 per planter. So here's another application. It says a small steel ball is dropped from a tower and will fall a distance of y feet in x seconds, as given approximately by the formula y, or f of x, equal to 16x squared. So the graph gives us the position at x equals 0 seconds, and then at x equals 1 second, at x equals 2 seconds, and x equals 3 seconds. And we have the distances of 16 feet, 64 feet, and 144 feet. Part A says find the average velocity from x equals 2 to x equals 3. So remember, average is equal to delta y over delta x. So what is the y value at x equals 3? That is 144. what is the y value at x equals 2? That is 64. And then the change in x. So for part A, we have 80 over 1, which is 80 feet per second. This is describing a measurement in feet. These are describing a measurement in seconds, and we get feet per second. Part B says find and simplify the average velocity from x equals 2 to x equals 2 plus h. This is when we want to use our formula that we had found earlier. We did the proof. Let's go back to that proof. Here it is. We started out with the slope formula, and we proved where this f of a plus h minus f of a all over h comes from. So for part B, we're going to say f of, and it's going to be 2 plus h minus f of 2 all over h. And our function is 16x squared, so we're going to say 16 times 2 plus h squared minus f minus 16 times 2 squared all over h. So we'll continue part B on another page here. 16 times 2 plus h squared. We have to FOIL 2 plus h times 2 plus h. And that gives us 4 plus 4h plus h squared. Don't forget, we still have to multiply this by 16. When we distribute the 16 through here, we have 64 plus 64h plus 16h squared. So that replaces this part of our equation. And over here, the 16 times 2 squared gives us a minus 64 with the whole thing over h. So we see the 64s are going to cancel. And we now have 64h plus 16h squared all over h. Notice that there are h's in each term in the numerator, so we should factor out an h since it is a common factor. And we see now the h's in the denominator will cancel with the h we factored in the numerator. And we are left with a simplified expression, 64 plus 16h. So part B says find and simplify the average velocity from x equals 2 to x equals 2 plus h seconds. And this would be our answer to part B. Part C says find the limit of the expression from part B as h approaches 0. The limit as h approaches 0 for 64 plus 16h. Well, this is a polynomial, so we can use direct substitution. Part C tells us that the limit is equal to 64. So now part D says discuss possible interpretations of the limit from part C. And remember, we're using h, where h represents the distance between 2 points. So as the distance between 2 points approaches 0, then that is giving us the distance at a singular point. And instead of average velocity over time, we're getting velocity at a moment. As h approaches 0, we are evaluating velocity at a given moment in time. So recall, h is the distance between 2 points x, and those points x are differences in time. So from 1 to 2 is 1 second difference, or from 1 to 3 is a 2-second difference. But we're saying as the difference in time gets closer and closer to 0, it is no longer an average velocity over time, but it is a velocity at a given moment, and what we will come to know as instantaneous velocity. So our definition for the instantaneous rate of change, where y is equal to f of x, the instantaneous rate of change at x equals a is given by this equation with the limit as h approaches 0 if the limit exists. And we continue by identifying the slope of a graph of a tangent line is also calculated with this derivative, which is the instantaneous rate of change. And we want to make a connection between types of geometric graphs. So instantaneous rate of change is slope of a tangent line average rate of change is the slope of a secant line. The instantaneous rate of change, we get 1 point on the function's curve, and the average rate of change, we get 2 points on the function's curve. And that is something we want to know the difference between, and it will affect how we approach a problem. Instantaneous rate of change versus average rate of change. Instantaneous gives us tangent line slope. The second derivative on this page The second definition on this page says for y equals f of x, we define the derivative of f at x, and we denote it as f with this mark we call prime. So we call this f prime of x. F prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0 if the limit exists. So the difference between the definition at the top and bottom is we have a constant a going in place of x for the top definition. We're getting a real number as our final result. And the bottom definition, we're going to leave the variable x in there, and we're going to get a function as our result. It says if f prime exists for each x in the open interval ab, then f is said to be differentiable over ab, but we want to identify f prime of x as a new function. So the derivative of a function f is a new function f prime. The domain of f prime is a subset of the domain of f, and the derivative has various applications and interpretations, including slope of a tangent line, instantaneous rate of change, and velocity of an object at time x. So here we have an example. Find f prime of x, known as the derivative of the function f at x, for the function f of x equals 4x minus x squared. They want us to use the 4-step procedure to find this derivative, and they give us these 4 steps to follow. So first evaluate f of x plus h. So that means replace all of the x's with x plus h. And we've done this in the past with the And we've done this in past sections where we've plugged in x plus h into a function and evaluated it. We've been preparing for this problem since chapter 1. So f of x plus h is equal to 4 parentheses x plus h minus x plus h squared. And the first part we just distribute to 4, but the second part we have to FOIL. F of x plus h is equal to 4x plus 4h minus parentheses, because anytime we follow a minus, we need parentheses, so we distribute that negative through. And when we FOIL x plus h, we do first, which is x squared, outer, which is plus xh, inner, which is plus another xh, and last, which is plus h squared. Let's write this in its simplest form. 4x plus 4h. Now I'm going to distribute this minus x squared. The xh plus xh is 2xh, so we have minus 2xh, and then minus h squared. And we see there's nothing we can combine here. That is going to stay as it is. Step 1 is done. Now we want to take this f of x plus h and subtract f of x from it. F of x plus h minus f of x is equal to everything we have up here. Minus, anytime we introduce something following a minus, we use parentheses so that we distribute that minus. And now we see we have 4x plus 4h minus x squared minus 2xh minus h squared. Distribute the negative, we have minus 4x. Distribute the negative, becomes plus x squared. And we should identify that the 4x's will cancel and that the x squareds will cancel, so that we can say that f of x plus h minus f of x is equal to everything left. So that is 4h minus 2xh minus h squared. So that is all we have left. We're going to put that into the numerator of step 3. So we have 4h minus 2xh minus h squared all over h. And step 4 asks that we evaluate this limit. So step 4, we have the limit as h goes to 0. We have an h in the denominator, and I see I can factor an h out of the numerator. That leaves me with 4 minus 2x minus h. These h's cancel, and I can plug this 0 into this last one to evaluate the limit, because that's a polynomial. And the end result is that f prime of x is equal to 4 minus 2x. And that is our new function using the 4-step process. We just found the derivative. And this will calculate the slope for tangent lines at any point on the graph of f of x where it is differentiable. Okay, so now we're going to find tangent line slopes. And we saw that we just found the tangent line function for f of x equals 4x minus x squared. And the answer we got was f prime equals 4 minus 2x. And we can now calculate tangent slope of the graph at any point by plugging into our derivative function. So part A says find the slope of the graph at x equals 0. Slope at x equals 0 is equal to f prime of 0. Well, f prime is 4 minus 2x. So it's 4 minus 2 times 0, and we get 4. That means slope at x equals 0 is 4, or 4 over 1. If we want slope at x equals 2, we evaluate f prime of 2, which is 4 minus 2 times 2, which is 0, and slope at x equal to 3, we evaluate f prime of 3, which gives us 4 minus 2 times 3, which is a slope of negative 2. Part B says graph the function 4x minus x squared and use the slopes found in Part A to make a rough sketch of the tangent lines to the graph at the locations x equals 0, x equals 2, and x equals 3. Okay, so here is a graph of our function, and we see that at x equals 0, that looks like the tangent slope at x equals 0. And at x equals 0, we had a slope of 4. Next, we want to look at x equals 2. So 1, 2. It looks like we get a slope of 0, a horizontal line. And we see that's what we got. And now at x equals 3, we expect a negative 2 slope. So 1, 2, 3. We have a line that goes down, so approximately a negative 2 slope. So this gives us our graph of our function and what the tangent lines would look like at each of those locations. And we see that we've calculated the slope for those locations, and those slopes make sense with the graph. Here's an example finding f prime of x, given that f of x is a rational function, 1 over x. So once again, we start with our f of x plus h. And then we evaluate f of x plus h minus f of x. And we see we have two fractions with different denominators. So we'll take each denominator and multiply the top and bottom of the other fraction by it. And now this gives us two fractions with the same denominator. Once the denominators match, you can combine the numerators. And then distribute that negative through. And now write the limit as h goes to 0 of f of x plus h minus f of x all over h. And now we see we have a complex fraction. So we rewrite it as the fraction divided by h is the same as a fraction multiplied by the reciprocal. And the limit as h goes to 0 of negative 1 over x times x plus h, we try direct substitution, and we see we don't get a problem. We get negative 1 over x squared, and that would be our derivative function. So f prime of x is equal to negative 1 over x squared. Here is an example finding f prime of x, the derivative of f, where f of x is the square root of x plus 2. Once again, we start with f of x plus h. and then f of x plus h minus f of x. And we distribute this negative through the second parentheses. And we see the 2's cancel. Now the limit as h goes to 0 of f of x plus h minus f of x all over h. So we see that we cannot plug 0 in for h because we would get 0 in the denominator. So we learned tricks in algebra when dealing with rational functions, and I can multiply this fraction by the square root of x plus h minus the square root of x, but I want to change it to a plus. If we take it with the opposite sign, it's going to rearrange itself nicely. And I'm allowed to do this because I'm multiplying the top and the bottom of a fraction by the same thing. So this is really just a fancy way of saying the number 1, because when the numerator and the denominator match, as long as the denominator is not 0, we will not get any problems here, and we can multiply and rearrange this and get the same function expressed in a different way. So when we FOIL the numerator, we will get x plus h minus x in the numerator, and the denominator will give us h times x plus h under a radical plus radical x. So if you look at this, the radicals will cancel, and then when we multiply the middle terms out, we will get opposite sign terms that cancel. Well, now we can see the numerator will cancel out the x's, and we're left with h over h times the square root of x plus h plus the square root of x. And now the h's cancel, leaving a 1 in the numerator. So the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now we can plug in 0 for h. It doesn't give us any problems. We get 1 over the square root of x plus the square root of x, which is 1 over 2 the square root of x. So our derivative, f prime of x, is equal to 1 over 2 times the square root of x. So here we want to look at when does the derivative not exist. And the book says the non-existence of a derivative at x equals a depends on the existence of a limit at x equals a. That is to say, the existence of this limit. Remember, the derivative is defined as a limit. So does the limit definition of the derivative exist at a point? If it doesn't, then the derivative doesn't exist at that point. If the limit does not exist at x equals a, we say the function is non-differentiable at the point x equals a, or f prime of a does not exist. So let's look at this graphically for a moment. Remember, the tangent line is the slope, which represents the derivative at a point of the function. And my blue curve here is my function f of x. And at this point, this would be f prime of a. And I can take another point here and say that this is f prime of b. And the f prime is the slope of the tangent line at that point. And f prime of a and f prime of b exist because we see there's a smooth transition from the left side and from the right side of each of these tangent lines and their points. Well, the derivative does not exist if we have a discontinuity So a function must be continuous at a point for the derivative to exist at the point. That's one criteria. The second criteria is it must be a smooth transition. So just to show an example here, the derivative does not exist at this point because what is the slope approaching on the left-hand side? We see that this is a slope of 0, a slope of a positive number, and the positive number keeps getting larger. On the left side, we have a positive slope. On the right side, we have a negative slope. And you can't say that the limit is equal if the left side is positive and the right side is negative. It's not a smooth transition. So these are all negative slopes coming down. So the derivative does not exist at sharp points in a graph or at discontinuities in a graph. So here we see some graphical examples. Discontinuity, so the derivative doesn't exist at A. Here we have, if you trace the function from the left side, it's negative, 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 all the way to this point, and then right on the other side of the point, the slope of the tangent lines are positive. Here's another example when the derivative doesn't exist. It's when the tangent line is vertical at a point. Remember, the derivative is slope of a tangent line, and a vertical slope is delta y over delta x, such that the denominator is 0, which is undefined. So the derivative does not exist at A in this example either. And here we see we have a cusp, vertical tangent line, no good. And here we see we have a vertical asymptote. This is a discontinuity, sharp point, vertical tangent line, sharp point, discontinuity. And we could even look at something like the absolute value function. And we would say at this point, the derivative does not exist. The left side has negative slope, the right side has positive slope. There's no smooth transition. But if we look at a parabola does a smooth transition. And the tangent slope would be 0. Here the tangent slope goes from a negative to a positive right at that point. Here we have a nice smooth transition to 0 and then to positive. So the derivative exists for a parabola. Or I should say for the vertex of a parabola. But the derivative does not exist for the vertex of the absolute value graph. But the derivative does not exist, D and E, for the vertex of the absolute value graph. So if we look at this problem here, So those are graphical ways we can interpret whether the derivative exists or not, or if we were to evaluate the limit numerically, the left side limit and the right side limit have to have a smooth transition of values and be continuous. So here's an example from the exercise section of the textbook. Number 46 says find the slope of the secant line joining 2, f of 2 and 4, f of 4. And we see here's our function definition. So f of 2 is equal to 2 squared plus 2, which is 4 plus 2, which is 6, which means that 2f of 2 is the same as writing 2, 6. Then we want to look at 4f of 4. So if we write f of 4 is 4 squared plus 4, this is 16 plus 4, which is 20. So the point for f of 4 is the same as writing the point 4, 20. 46 says find the slope of the secant line that joins these 2 points, and that's just the slope formula. 20 minus 6 over 4 minus 2 gives us 14 over 2, which is a slope of 7. I'm going to add to this m, because m is from y equals mx plus b. It is the letter used for slope. And in the subscript, I put secant, which is 7. This is to help us know this is secant slope. And just to remind us that secant slope is the average rate of change over an interval. What is the interval? Well, the interval is from 2 to 4 in the domain of this function. That's part A. And to contrast that, part C says find the slope of the tangent line at 2, f of 2. So the slope of the tangent line means we want to find f prime of x, and you're going to use the limit as h goes to 0 of f of x plus h minus f of x all over h. And when you do this, the answer you should get is 2x plus 1. So if f prime of x is equal to 2x plus 1, then f prime of 2 would give us the slope of the tangent line at this point. And when we plug 2 in for x, we get 2 times 2 plus 1, which is 5. And I'm going to use m for slope with a subscript of tangent equals 5. And just as this was the average rate of change for secant, this is the instantaneous rate of change when we use tangent. So once we have the slope at this point, and we have a point on the graph, once you have a slope and a point, you can write a linear equation, and part D asks that we write the tangent line equation. Okay, so we want to write the tangent line equation. We've already found that the slope at this point is 5. We just have to find the y value, so we have to plug 2 into our function, and we see that f of 2 is 6. So we use the point slope formula. Which says y minus y1 equals m times x minus x1, where x1 and y1 are the coordinates of a known point, and m is the slope. So we get y minus, here's our known coordinate for the y slope, so it's 6, y minus 6 equals, our slope is 5, times x minus, and the x coordinate we're using is 2. So this is the point slope form, and we can distribute the 5 through here. This gives us y minus 6 equals 5x minus 10. And now we can add 6 to both sides. If we needed the slope-intercept form, we can rearrange the point slope easily and get that the tangent line equation is y equals 5x minus 4. So this is the tangent line to f of x at x equals 2. And we see it would go through -4 on the y-axis and has a slope of 5. So it goes up 5 and over 1 through the coordinate plane. And this is how you would graph the tangent line with the function f of x. Here's another problem from the exercise section, and it says, refer to the graph of the function f as shown, and use the graph to determine whether f prime exists at each indicated value of x. So number 49, we find a, and we come up here and we say there's a solid point, so there's no hole, it's continuous, and the tangent lines have a smooth transition on both sides of that point, so we say yes, it exists at x equals a. At number 50, x equals b, we see that the tangent line does not exist at this point because the left limit and the right limit, even though they're equal, we have a discontinuity at this point. So the derivative does not exist at x equals b, so we say no. Number 51, x equals c, we have a vertical tangent line, so the slope is undefined for the tangent line, so we say no. At d, the slope is 0, there's a smooth transition from left to right, and the point exists, so the function is continuous, so we say yes, the derivative exists there. Again, the derivative exists at e, so yes. At f, we have a sharp change in slope, it's not smooth, so we say no, the derivative is undefined, we don't have a smooth transition. At g, we see that, and just to give you an example of what it looks like at g, it goes like this at g, so that's a smooth transition and it's continuous, so we say yes, it exists. And for the last one, we have a cusp with a vertical tangent line. We say no, the derivative does not exist. So that is the end of this lesson. Watch the video, take notes, complete the practice, and come to class with questions.